So, for today, we'll be discussing about the Stokes law, and we'll also discuss all the everything about the fluids that we discussed up to now. So, Stokes law, it determines or it tells us about the fluid friction. It's related with the fluid friction. Since the fluids also offer friction, the friction offered by fluids is called as fluid friction. So we write here the friction offered by fluids. The friction offered by fluids is called as fluid friction, and what are the factors on which the fluid friction depends? So we'll see what are the different factors on which the fluid friction depends. So yesterday we had discussed about viscosity, another term, which was relating to the fluids only. We discussed yesterday about two things. We discussed about surface tension and elasticity, viscosity. Surface tension and viscosity. On this Sunday, you will be having a test which will include we will be including the basics, that is the units and dimensions that will be included for the test, speed, velocity, and rotation. So up to rotation, you will find the questions in your Sunday's test. So this Sunday we'll put up a test of regarding nearly 60 marks. Now, so can you define surface tension? Yes,
The
just one.
property of the fluid that in which the upper surface of the fluid behaves as
Mhm.
a stretched membrane.
Yeah, it is the property of a fluid by which the surface of a fluid behaves as a stretched membrane, and it is due to the surface tension because of which we observe certain phenomena that are occurring. For example, the capillary action is due to the surface tension, the closing of the bristles, formation of water as a droplet. Like why water drops are spherical in shape. That is also a reason, surface tension. So otherwise, if had there been no surface tension, so water droplets could gain any shape. But if you observe the water
Yes.
droplet, they have a spherical shape. And I explained you the reason yesterday that for the spherical shape, sphere has the minimum surface for a given volume. So hence, a surface or fluid surface, it has a tendency to occupy the minimum surface area. That is because of its surface tension. Then next we discussed about the viscosity. Viscosity tells us about the friction between the layers of liquids. It actually tells you that how the fluid can flow. That means the different layers of liquid, they offer resistive forces which will be called as viscous liquids. So if you compare water, honey, and so on, so honey is likely to be more viscous than water. So that we call as viscosity. Here we come across a formula in terms of viscosity. We write the viscous force or viscous force by a fluid is equal to minus eta A multiplied dV by dx. dV by dx is a relationship. This is called as a velocity gradient.
Gradient. Yes.
Yeah, so this is velocity gradient, dV by dx. Velocity gradient, it represents how fast velocity changes with respect to time. So you might have seen this symbol first time, like you generally have seen V by X or V by T, okay, or delta V by delta T.
You had
That's
given
what,
this for dimensions also, sir.
yes. So I had given this for dimensions, just explaining this meaning dV by dx. So the symbol, suppose I want to find acceleration. So acceleration is written as change of velocity by time. We write it as delta V by delta T. This is how we write the acceleration. But if suppose our time period for which we are observing is very small, if the time for which we are observing tends to zero, it tends to zero. It's not actually zero, it tends to be zero. It tries to become zero. So for that case, we write that becomes a special case of mathematics. And write this using the symbol d by dt of v, or we read it as dv by dt. This is also called as first derivative of velocity. D by dt or d by dx, it is the first derivative. So you will be studying this in mathematics, that d by dx is an operation. It is a special type of mathematics which we call as calculus. So when the time or when the denominator turns out to be very, very small, it turns out to be almost tending to zero. So that property, at that point, we evaluate the function which we call as the dv by dx, or derivative of a function. Okay. So think acceleration, in terms of acceleration, in the same way you can write velocity also as dx by dt. Velocity in the x direction will be written as dx by dt. Velocity, we write it as vx equals to dx by dt. Velocity in the y direction will be written as vy equals to dy by dt. So the symbol dx by dt and dy by dt, they give you the instantaneous values. Okay. So this is how we find out the instantaneous value of the velocity. Instantaneous value means at the exactly at that time what was the velocity, so that we call as the instantaneous value of the velocity. Okay, so similarly here also dv by dx, it represents the first derivative of velocity. So how the velocity changes with distance. For example, if we observe a number of layers, yesterday we did like this. A fluid consists of a number of layers. So here you have a number of layers, and these layers, if you observe, the upper layer moves quickly, and this layer tries to move the bottom layer. It tries to move the bottom layer, and the bottom layer offers friction. Okay, so as a result, in the similar way, the next layer and then the next layer. So what happens here, this will be velocity v, and this will be a velocity something less than this. This will be velocity something less than this. So as we are moving along the distance, let this be the x, velocity is decreasing. So we find here velocity gradient, the decrease of velocity with distance. Okay, and since the velocity is decreasing, therefore we use here a negative sign. We use here a negative sign since the velocity is decreasing. Had it been increasing, then we would have used here a positive sign. Okay, so that is why f equals to minus eta a dv by dx. Here eta represents, this is the symbol eta, it represents coefficient of viscosity. So it is coefficient of viscosity. Now the other terms. Today we have to discuss about the Stokes law. So yes, in the past classes we have also discussed about terminal velocity, a phenomena which is related with the Stokes law. Actually, terminal velocity is the resultant of the Stokes law. So let us see today's Stokes law, and we'll also see the fluid friction. So as we observe that fluid friction is the friction offered by the fluids, and as per the Stokes law, if you the Stokes law define that on what factors, what are the factors on which the fluid friction depends. Okay, so fluid friction offered by the fluids, the factors on which the fluid friction depends, they are shape of the body. So fluid friction depends on shape of the body. It also depends on speed of the body. So speed with which the body moves. It also depends on size of the body. So shape and size and speed of the body. These are the factors on which the fluid friction depends. Now, a combination of all these is given by the Stokes law. Let's see what the Stokes law says. Just one.
Sure, sure.
Can you turn on the camera? Okay, Stokes law. The fluid friction is proportional to so the fluid friction offered by a substance is proportional to coefficient of viscosity. Then it is also proportional to radius, that is the size, and velocity. So if a body starts moving faster, it will experience greater amount of the fluid friction. So here we consider a moving of a ball through air. Suppose we have an example of a ball being dropped through air. So we have a ball dropped through air. Now when the ball passes through the layers of air, it experiences a backward dragging force. And the amount of the dragging force experienced or amount of the friction, since the ball is moving in the downward direction, we can observe that the ball moves in the downward direction. This is the direction of motion. It's moving in the downward direction. So the backward force that it will experience, okay, so here the backward dragging force, the dragging force will be opposite to the direction of velocity. So here you will have the backward dragging force which is upward and it's moving in the downward direction. We also know that the gravitational force or the weight of the body, it acts in the downward direction. So in this situation, you have two forces acting on this ball. The two forces which act here, they are the frictional force acting upward. We have the frictional force acting upward and the gravitational pull acting downward. So you have gravitational pull that acts downward. You have the frictional force which acts upward. Now, the problem is that the frictional force, it depends on the velocity. The formula for the frictional force is given as F equals 6 pi eta R and V. So see, this force, it depends on the properties of the material that is there, that is coefficient of viscosity. It depends on the size and it depends on the velocity. So if the speed of the ball increases, so there will be greater amount of the frictional force. There will be greater amount of frictional force offered by the air. Okay. So a stage will come if the speed increases. So a stage will come that this upward force or frictional force will be so high that it will be equal to the gravitational pull. Are you getting this concept? When the speed increases, the frictional force increases, and a stage comes where the frictional force will be equal to the gravitational pull of the object. You can observe such a thing similar to this thing. Suppose you are cycling through, if you are cycling and a fast wind is blowing opposite to you, so you will experience a greater amount of frictional force to cross that air. So a similar thing happens here also. The ball is passing through the air, and since motion is relative, whether air is moving or whether the ball is moving, it's the same thing. It's the ball moving through air or it's air moving and ball is standing over there. So both are same thing. There will be same amount of frictional force. So the frictional force would be equal to 6 pi eta Rv. If the speed increases, so a point will come that these two forces will be equal to each other. And hence, the ball will experience no net force. So what do you think when no net force act, or at a point when we observe that the frictional force and gravitational forces, they are equal to each other? So what should happen at that point? Should the ball stand over there only? Jaswant,
Sir,
what should happen? Should the ball stand there only? When the frictional force equals the gravitational pull, so what should happen to the ball then? Should it stand there?
should
Yeah, Shreyasi, what should happen? Should the ball stand there or should it move? Shreyasi, you are muted.
Yes, sir. Yes, sir.
Okay. So can you think what will happen?
the ball will move.
The ball will move. Why the ball will move if the net force is equal to 0 here? Here we obtain that the net force is equals to 0. So shall the ball move?
No, sir.
Force
See,
is zero, sir, but due to
mhm, due to, correct, almost correct.
gravitational pull.
No, the gravitational pull is equal to the force, frictional force. So there is no net force. Gravitational force
Okay.
has been balanced. Then see, the ball will move down. The reason is that it's already in motion. It is having some velocity.
All right.
Okay, it's having some velocity. So due to inertia of motion, it will continue to move with constant velocity. So the ball will continue to move with constant velocity. The work of force is just to provide acceleration. If the net force is 0, so we'll say force is equals to mass times acceleration. And if the net force is 0, so we will say here that acceleration is 0. So acceleration is 0, but still the ball can be in motion. It can move with the constant velocity. There will not be any change of velocity. It will move with a constant velocity. Got it?
Yes, sir.
Okay. So what name is given to that constant velocity? Is that velocity given some any name? Try to recall. We have studied.
Sir, I don't know.
Okay.
Momentum.
No. We call that terminal velocity. That is the terminal
Yeah.
velocity. Okay. So
Sir, I
terminal.
haven't reached there, so that's why.
Okay. So terminal velocity is the maximum velocity attained by an object which passes through a fluid. So this is the maximum velocity that it has attained. Gravitational force is same. So the maximum velocity has reached. Beyond this, its velocity cannot increase. The reason being that the gravitational force has been balanced by the backward dragging force. So we say that it has reached a terminal velocity. And I gave you the example that the raindrops which are falling, the raindrops will be falling and hitting us with the speed of around 100 meter per second or 200 meter per second. Considering a cloud to be located only at about 400 meters, if suppose the clouds are located only at 400 meters, then also the speed with which the raindrops will hit the ground, it will be around 100 or 200 meter per second, which are which the speed is fair enough to pass through us. So you have seen about water jets. Water jets can be used to cut different materials. So the rainfall would appear like a water jet had there not been this viscous drag, had there not been this dragging force. And this is the region that we have studied, that acceleration due to gravity is constant, that a heavy object and a light object will fall with the same speed. Right? We have studied, but we are not able to get it practically. The region is this backward dragging force. The backward dragging force, which depends on radius, which depends on velocity, which depends on coefficient of viscosity. Okay. So, got this?
Yes, sir.
Yes. So this is the region.
Yes, sir.
If this is the region that both a heavy object and a light object will fall at different times. They will take different time to fall off. The region is just the backward dragging force. And this backward dragging force is calculated as F equals 6 pi eta RV. So this backward dragging force is given by the Stokes law. We call this law as the Stokes law. As per the Stokes law, the fluid friction is proportional to the coefficient of viscosity, radius, and velocity. So the radius of the object that is falling and the velocity of the substance that is falling. These are the factors on which the backward dragging force depends. And this is the same region that if you try to accelerate with your vehicle, so there is a certain maximum speed beyond which you cannot accelerate. You cannot accelerate your vehicle beyond a certain limit. Why the region? The region is again the dragging force that is acting. The viscous force that acts on the vehicle, it increases with velocity. So if you increase the velocity of your car, the backward dragging force will also increase. Okay. So a point comes when the power of your engine equals the backward dragging force, and hence even if you are not able to accelerate beyond that limit. And since it depends on the shape and size of the object, here we have used R if the object is spherical in shape. Considering the object to be spherical in shape, we have obtained the formula F equals to 6 pi eta RV. Okay. Now, similar to this, if there is different shapes can be given to reduce the amount of fluid friction. For example, we have seen the design of car and the design of bus are different. Okay. A bus is designed straightforward, something like this. A car is designed like this. A car has a different design like this. Okay. So an aerodynamic shape is given to the car so as it can drive at a higher speeds, so that it offers or air offers minimum friction to the car. Whereas trucks and other buses, they are designed to operate or move at a not at a very fast speed. They are designed to move at some minimum at some lesser speeds. Okay. Any other doubts to anyone?
No,
I
sir.
think okay. I think today you have understood all the concepts of this fluid. So the concepts of fluid have been understood. Yeah, just from the solids, we had studied about the Hooke's law. So just giving you a quick revision of the Hooke's law also. So do you remember about the Hooke's law?
I did not reach there, sir.
Okay.
Yes, sir.
So just once, can you tell about the Hooke's law?
Sir, RF signed it.
Yes, the restoring force developed in a spring is directly proportional to the extension produced. Yes, extension produced. So this was regarding the Hooke's law. Hooke's law means it's not only the spring, it can be any object. So all the objects which are there, they develop a restoring force if a certain amount of force is applied on them. If a force in equilibrium is applied on them, so a restoring force is developed, and that restoring force is directly proportional to the extension produced. By extension, we mean that there can be different types of modifications in shape that can appear. For example, there can be change in there can be a bending that has been achieved. There can be an extension that has been achieved. For example, something like this. Consider a iron rod. So suppose you have an iron rod like this. You have an iron rod, and suppose you apply some amount of force on the top like this, and make this iron rod bend somewhere like this. So suppose you make it bend like this. You make it bend. And now if you release it from here, if you release this from here, so it will regain its original shape. It will try to come to its original shape, and hence it will start vibrating. Okay. So here here we have talked of a different type of strain, a different type of change that has been produced. Here in the Hooke's law, we are at this point we are talking of the extension. Talking of extension means it's something like this. Suppose if you have an iron rod, and from that iron rod you hang some mass, you hang some heavy mass with it at the bottom. So if you hang any mass at the bottom, there will be a change of length. A new length would be added to it. Its length will increase. Okay. So this phenomena is called as Hooke's law. And as per the Hooke's law, since change of length is delta L, so as per the Hooke's law, we'll write F is proportional to X or delta L. So this phenomena, however, this is not observable in reality. But yes, if you take a thinner iron piece, you will be able to observe, or you can observe it better with the help of a spring. So if you have a spring, in the spring, this phenomena is observable. So you can take a spring, and on the spring, if you hang some mass, so definitely its length will change. You hang some mass on this, so its
Yes.
length will change. There will be some extension produced X. So hence the force or the restoring force, the spring would not like to remain in the same position. The spring will have a tendency to move in the backward direction, to come to its original state. So because of which a restoring force is set up in this spring, and that restoring force F is given by F will be proportional to X, that is the extension. So we write it as F equals Kx. Here, K represents
K
the
is
spring
the
constant.
constant.
Yeah, it
Okay.
is also, it's called as spring constant or force constant.
Yes.
It's called spring constant or force constant. The values of K, they depend on the geometry of the spring. They depend on the type of the spring. They depend on the material of the spring. Also, the Hooke's law is obeyed only up to a certain limit. Hooke's law has a certain limit. Limit means the Hooke's law is valued or is valid only up to the elastic limit. Okay. Are you there all? And am I audible?
Yeah, yes, sir.
Okay. Because I certainly observed certain change being occurring. So that's why I. So we had seen some questions which were based on the Hooke's law. We will see one more question which is based on the Hooke's law. So let's see. Let's try to add one question here. A spring of length a spring of length 12 centimeter is extended to 15 centimeter by putting a mass of 50 gram. Find the extension produced if the spring find the find the extension produced if the spring is loaded with 70 gram. Okay. So I expect you will try to attempt this question. You can note down this question, attempt this question as a homework.
Yeah, okay, sir.
So this question is a part of your homework. Okay, bye. See you tomorrow.
Bye, sir. Thank you, sir.